Let's start looking at some of the rest of the curves. Y equal to x power 4 by 1 plus x whole cubed. All right. Do you see some roots here? 0 is a root. Repeated 4 times. So its dy dx must also become 0 at x equal to 0, right? So you perhaps in for either a local maxima or a local minima at x equal to 0. We'll check that out later, right? Then, do you see an asymptote? X equal to minus 1. Right? Let's differentiate this with respect to x, right? And examine for x equal to 0. Right? See 4x cubed into 1 plus x whole cube minus 3 into 1 plus x whole squared into x power 4, isn't it? So, I could, let's say, take x cubed common from this, x cubed common from this, and 1 plus x whole cubed could be cancelled from numerator and denominator. 1 plus x whole squared could be cancelled. So this will become 3x power 4. So this will become x power 4, right? 1 plus x whole squared cancel. So x cubed 4 into 1 plus x minus 3 divided by 1 plus x whole to power 4 minus 3x, minus 3x. So which is like x cubed into x plus 4 divided by 1 plus x power 4, right? Now, dy dx is becoming 0 at x equal to 0 and at x equal to minus 4. Now, what about x equal to 0? When x is slightly less than 0, this will be negative. When x is slightly greater than 0, it will be positive. So x equal to 0 must be a local minimum. X equal to 0 must be a local minimum, isn't it? Right? X equal to 0 turns out to be a local minimum. And then, even without checking, you can say x equal to minus 4 must be a local maximum. Local maximum, right? Now, let's start putting it all in place. This is the asymptote x equal to minus 1. This is the asymptote x equal to minus 1, right? Do you also see that as x tends to minus 1 from the greater than minus 1 side, y tends to plus infinity? Y would tend to plus infinity? That means you would expect this to happen. At x equal to 0, not only is y 0, but dy dx is also 0 at x equal to 0. And we have seen that at x equal to 0, see, if it is coming this way, then we actually expect a local minimum at x equal to 0, right? A local minimum at x equal to 0. And then after 0, there would be no turning point. So it will go this way, right? Okay. Now x equal to minus 4 is a point here, right? At x equal to minus 4, y is negative. At x equal to minus 4, y is negative. So y is somewhere here. And not only that, it has a local maximum at x equal to minus 4. So you would expect something like this. At x equal to minus 4, a local maximum. Yes or no? Right? Now, as x tends to minus 1 from the less than minus 1 side. As x tends to minus 1 from the less than minus 1 side, do you realize that y would tend to minus infinity? Right? Right? Yes or no? Now, given this, let's see if there are asymptotes to the curve that are inclined. This was a vertical asymptote x equal to minus 1. To refine the curve, let me check if there are inclined asymptotes to the curve. But this seems all right, right? This seems all right. So far, so good, right? Now, can I wipe this off? Can I wipe this off? Say there is an inclined asymptote. Which is y equal to mx plus c. And if you remember, if that be this is y equal to fx, then if an m exists, then m must be limit fx by x as x tends to, let's say, plus minus infinity. That must be the slope, right? Fx by x means x cubed by 1 plus x whole cubed as x tends to plus minus infinity. And what is this limit equal to? 1. You divide by x cubed numerator and denominator, you will get this limit as 1. So m turns out to be 1. Right? What would fx be? Fx would be, what would c be? C would be limit x tends to infinity fx minus mx. Fx minus mx, right? So if there exists a c, then that c must be limit fx minus mx as x tends to plus minus infinity. Yes or no? Which is to say, c must be limit fx, which is x power 4 by 1 plus x whole cubed minus x as x tends to infinity plus minus infinity, as x tends to plus minus infinity. M is 1 here, isn't it? What is this limit? X power 4 minus x into 1 plus x whole cubed divided by 1 plus x whole cubed, x tends to plus minus infinity, right? X power 4 will get cancelled, so you will have minus x into 1 plus 3x plus 3x squared divided by 1 plus x whole cube as x tends to plus minus infinity, right? Isn't it? Now, if you divide both numerator denominator by x cubed, if you divide numerator denominator by x cubed, what would you get? Limit 1 minus minus of 1 by x squared plus 3 by x plus 3 divided by 1 by x plus 1 whole cubed as x tends to plus minus infinity, right, which is minus 3. See, turns out to be minus 3, as you can see, right. So there is an inclined asymptote, and the inclined asymptote for this curve, is y equal to x minus 3. X minus 3 is the inclined asymptote. Now let's refine this curve. This was good enough, but let's get a superior look of the curve. So let me first draw the two asymptotes and redefine this, refine this, the looks of the curve. Okay, but so far so good. I hope all of you have understood these calculations here, right? Let me first draw the two asymptotes and redraw this curve. Y equal to x minus 3 is this asymptote. C is minus 3. This is y equal to x minus 3. Is an asymptote. As x tends to plus or minus infinity, the curve tends to y equal to x minus 3, right? There is a vertical asymptote, which is x equal to minus 1 is a vertical asymptote. Okay. Now everything else remaining the same. We will not redo our calculations. Let me draw the curve. See, it's going this way, beautifully merging with y equal to x minus 3 in the long run, right? And x equal to minus 4 must be somewhere here. Again, as x tends to minus infinity, y tends to x minus 3. So this must be x equal to minus 4, a local maxima. A local maxima at x equal to minus 4. This is a refined look of the same curve. What do you say? है ना? Got me? Let's draw the next one. Clear, na? Y equal to 2x minus 1 plus 1 by x plus 1. Okay. Very readily, what are the two things you could say? Right, right. X equal to minus 1 is a vertical asymptote and 2x minus 1 is a inclined asymptote. Right, let's first do that. What's readily available? X minus 1 must be something like this, right? This must be y equal to 2x minus 1. And this must be x equal to minus 1. A vertical asymptote. This much at least, right? Now let me find the roots of this. Let me find the values of x for which y becomes 0, right? 2x minus 1 into x plus 1 plus 1 will be 0 for roots. These would be the values of x for which y becomes 0. So this is like 2x squared plus 2x minus x plus x equal to 0, or x into 2x plus 1 is 0, x equal to 0 and minus half. Yeah, x equal to 0 and minus half of the roots, right? Did you get this? 0 and minus half are the roots? Yes or no? So this is x equal to 0, and say x equal to minus half will be somewhere here. X equal to minus half will be somewhere here. These are the two roots, right? Now, few things very readily. Can I remove this? 0 and minus half are the roots. So one thing, between 0 and minus half, I would either expect a loop like this or I would expect a loop like this. Yes or no? Which means between 0 and minus half, I would expect at least a local maximum or at least a local minimum. Yes or no? Isn't it? Now, as x tends to minus 1 from the greater than minus 1 side. Okay? This tends to plus infinity. This tends to plus infinity, and this will be a finite number. So the whole thing tends to plus infinity, right? The whole thing tends to plus infinity, which means you would expect something like this, right? Yes or no? And therefore, chances are that even without doing too much, I can say that if this must be going this way, and a local minimum, and must be going this way. Can I say that? Even without differentiating, I'm expecting between minus half and 0 a local minimum. A local minimum is what I'm expecting between minus half and 0. Right? And as x tends to minus, so as x tends to minus 1 from the greater than minus 1 side, y tends to plus infinity. As x tends to minus 1 from the less than minus 1 side, from the less than minus 1 side, this will tend to minus infinity. This is a finite number, so the whole thing will tend to minus infinity. So I would expect something like this. And this again being an asymptote, I would expect a local maximum to appear somewhere here. So I would expect, I would expect a local minimum here, and I would expect a local maximum. A local minimum to the right of minus half and to the left of 0, and a local maximum to the left of minus 1 is what I'm expecting in this graph. Are you okay with this? Let's differentiate to just confirm our understanding. dy dx is 2 minus 1 by x plus 1 whole square. Right? dy dx will be 0 when 1 plus x whole squared is a half, or 1 plus x is plus minus 1 by root 2, or when x is, so dy dx is 0 when x is minus 1 plus minus 1 by root 2. Hey, minus 1 by root 2 must be to the left of minus 1. That means, this must be minus 1 by root 2, where you would expect a local maximum, and minus 1 plus 1 by root 2 must be here. See, one thing, minus 1 plus 1 by root 2, minus 1 plus 1 by root 2 is like minus 1 plus 0.7, roughly 0.7. So minus 0.3 roughly, minus 0.3 is obviously between minus half and 0, isn't it? So I would expect a local minimum here, I would expect a local maximum there, and therefore putting all of this in place in one shot at x equal to 0, this is what I would expect, right? And on this part at minus 1 by root 2, I would expect something like this. This is minus 1 by root 2. I would expect a local maximum, right? This is the graph of the function, isn't it? complete graph of the function. Hello. Let me look at the next one. Y squared is x power 4 into x plus 1. Okay, very quickly, what are the things that you can... Huh? 0 and minus 1 are the roots. And 0 is a repeated root. Huh? How to? কি খোকা এই মালটা শেষ হয়ে যাচ্ছে -1 এ 0 একটা রুট এর জন্য x equal to 0 একটা root, right? Now there are two roots. In fact, y equal to x squared plus minus x squared root x plus 1, so -1. Okay, now even powers of x, even powers of y, so symmetric about the x axis. Also, when x is less than -1, y square will become negative. So x less than -1 is not possible, because for x less than -1 this number becomes negative, but y square cannot be negative. That means the graph does not exist to the left of -1. The graph does not exist. That means will exist from x equal to -1 to the right only. Will not exist to the left of -1, right? These are some very simple, readily available conclusions. No part of the graph will exist to the left of -1. There is a root at -1, there is a root at 0. You would therefore expect a loop here and a loop here because of symmetry about the x axis, right? So in any case, between -1 and 0 you would expect a turning point, right? Isn't it? If there is a loop, at least one turning point between -1 and 0 is what you will expect. So let's differentiate. Let's differentiate to examine a critical point, a turning point. Dy dx, 2y dy dx, 4x cubed into x plus 1 by plus x power 4, which is like x cubed into 4 into x plus 1 plus x, which is x cubed into 5x plus 4. Dy dx is becoming 0 at x equal to 0 and at x equal to minus 4 by 5. And x equal to minus 4 by 5 is indeed a point here, right? And can I then say that at x equal to 0 you would expect something like this, and because of symmetry about the x-axis you would expect something like this, dy dx again becoming 0 at x equal to 0, right? And then as x becomes larger and larger, y would become larger and larger. It will take up shape like this, go this way. Yes or no? Got me now? See, as x tends to infinity, then y tends to infinity. As x tends to infinity, y tends to infinity. This would be the shape of the curve. Let me draw this. One minus x to power 2 by 3 whole to power 3 by 2. Even powers of x. Symmetric about the y-axis. And this could have been written as y squared is 1 minus x to power 2 by 3 whole to power 3. So symmetric about the x-axis also. It's symmetric about both axes, x-axis and y-axis, right? I hope you realize why I said this. Right, because when you square, you get y squared is 1 minus x to power 2 by 3 whole cube. So even powers of y. In fact, no. It's symmetric only about the y-axis. Because see, I don't have the luxury, I don't really have the luxury to square and get an even power of y. See, when I square, I am forcing an even power of y, but which is not the case. So I can't square. That will be unnecessarily creating symmetry about, see, when I have a line y equal to x, I can't say y squared is x squared and even powers of y is so symmetric about the x-axis. I can't say this, isn't it? So I can't square and say that it's symmetric about the x-axis. All that I can say is it's symmetric about y-axis. Why? Because there are even powers of x. Because there are even powers of x. Yes or no? Also, do you realize that x must lie between -1 and +1 only? Because x to power 3 by 2 must lie between -1 and +1. I mean, in the sense, x to power 2 by 3 must be less than 1, must be numerically less than 1. Yes or no? Because you have a square root there. So this can't be greater than 0. This can't be greater than 0. Yes or no? This can't be less than 0. I'm so sorry. This can't be less than 0. So for sure, x must lie between -1 to +1 only. X must lie from -1 to +1 only. Right? Let me draw the graph only in the first quadrant, because then I can reflect it about the y-axis. So for x greater than 0, it also has to be less than 1. For x greater than 0, it also has to be less than 1, because 1 minus this has to be greater than 0, because 1 minus this has to be greater than 0, right? So if this has to be greater than 0, why? Because there is a square root sitting there. You can't make this number negative. And for this to be greater than 0, x must be less than 1. Yes or no? Because if x is greater than 1, then x to power 2 by 3 will be greater than 1. This will become a negative number, and then you can't find a real square root of that. Right? So x has to be less than 1 if it is greater than 0. Right? So in the first quadrant, the graph exists. In the first quadrant, the graph exists only between 0 and 1. Only between 0 and 1. At x equal to 0, y is 1. At x equal to 0, y is 1. At x equal to 1, y is 0. Right? So these are 2 points on the graph. Now, between these two, you could either have something like this, or you could have something like this. Right? Let's see what happens. So for that, we need to differentiate with respect to x. We need to differentiate with respect to x. So if I differentiate with respect to x, this is what I get, isn't it? minus 1 by 3, sorry, minus 1 by 3, right? This is what I get, right? Now see, at x equal to 1, dy dx is becoming 0. At x equal to 1, dy dx is becoming 0. So would you realize that at x equal to 1, it's going this way? And that's the only value of x where dy dx is becoming 0. And y is positive for x lying in the interval 0 to 1. Y is always positive. Do you realize that y is always a positive number here? Therefore, at x equal to 1, dy dx is becoming 0. So you would expect something like this here. And therefore, in line with this, you would expect something like this to happen between 0 and 1. Yes or no? And at x equal to 1, at x equal to 0, see, this will come in the denominator, x to power 1/3 will come in the denominator. Dy dx tends to infinity as x tends to 0, right? See, which is what is happening. See, this could be written as minus 1 minus x to power 2 by 3 whole to power half divided by x to power 1/3. See, as x tends to 0, dy dx tends to plus infinity, isn't it? See, which is what it is. As x tends to 0, dy dx is becoming vertical. Plus infinity is vertical, isn't it? So which is what it is, which is how it's, right? Yes or no? And it's symmetric about the y-axis. Why? Because even parts of x. And therefore, you would expect something like this. Which part? See, dy dx is 0 at x equal to 1. 0 at x equal to 1. At x equal to 0, realize that it's minus infinity. Very large. Dy dx is very large at x equal to 0. That means very large dy dx means very large slope of the tangent, means a vertical tangent at x equal to 0. The tangent at x equal to 0 is purely vertical, therefore. And then it enjoys symmetry about the y-axis. Why? Because there are even powers of x, and therefore this would be the trace. What do you say? Right? This would be the graph of y equal to this. However, if someone said, draw the graph of y squared equal to 1 minus x to power 2/3 whole to power 3 by 3, then it will be the same except that this would get added. If someone said, draw the graph of this, then it would also be symmetric about the x-axis because there are even powers of y, and in addition to these two, this will also get added. This will also get added. Got me now? No? Right? So far so good, right? Readily, what can you say? There are two, yes. Right away you say the asymptotes. There is an inclined asymptote, which is y equal to x, isn't it? And there is a vertical asymptote, which is x equal to 0, which is the y-axis, isn't it? X equal to 0 is a vertical asymptote, and y equal to x is an inclined asymptote. Let me first draw the asymptotes. This is y equal to x, an inclined asymptote, and the y-axis is also an asymptote, right? Isn't it? Now, what is dy dx? See, there are no roots of this because x square plus 1 will never be 0. So no roots, no real roots, that is to say, of this. dy dx is 1 minus 1 by x squared, and dy dx becomes 0 at x equal to plus minus 1. dy dx will become 0 at x equal to plus minus 1. Now, see, as x tends to 0 from the greater than 0 side. As x tends to 0 from the greater than 0 side, this will tend to plus infinity, this will tend to plus infinity. So the whole thing will tend to plus infinity. And while doing so, it will encounter a turning point at x equal to 1, right? It will encounter a turning point at x equal to 1, it will turn around and flush with y equal to x in the long run. This is what it will do, right? In fact, we could have said x plus 1 by x for x greater than 0 is always greater than or equal to 2. At x equal to 1, therefore, we would have expected a minimum value of this, isn't it? So even without differentiating, we could have said that, well, okay, this length is 2 units at x equal to 1. Right, Aditya? Huh? One more thing. If you replace x by minus x, y becomes minus y, isn't it? If you replace x by minus x, y becomes minus y. Therefore, if x comma y is a point, minus x comma minus y will also be a point on the curve. And therefore, it's going to be symmetric about the origin in opposite quadrants. Symmetric about the origin in opposite quadrants. And this is where you see this other point minus 1 where dy dx becomes 0. This is the trace. Right? This is the trace of x plus 1 by x. Got me now? Yes, please. Haan, bolo. Haan. You have a class. Okay. Wait for one more problem after this. Let's draw the graph of this. I could write it like this, isn't it? X plus 2 minus 1 by x, 2 asymptotes. Y equal to x plus 2 and x equal to 0. That means the y-axis is an asymptote, right? The two asymptotes are, one is x equal to 0, which is the y-axis, and the other one is y equal to x plus 2, which is an inclined asymptote. So let me first draw the asymptotes. The y-axis, which we anyways have to draw. This is an asymptote. Y equal to x plus 2 is this line. Right? What is dy dx? 1 plus 1 by x squared, which is positive for all x. Which is positive for all x. That means the function is, wherever defined, it's only increasing. Right? And as x tends to 0 from the greater than 0 side, as x tends to 0 from the greater than 0 side, this minus 1 by x will tend to minus infinity. So y tends to minus infinity, yes or no? As x tends to 0 from the greater than 0 side, right? Therefore, greater than 0 side, y tends to minus infinity. No other turning point, it's going to go on increasing. It goes on increasing, does this, boom. This is how it goes. And therefore, you would expect one root of this somewhere here, which you can obtain by x square plus 2x minus 1 equal to 0 will give you two roots, one positive and one negative root. Why? Because the product of the roots is negative. So the positive root is obtained here. So one root will be positive, the other root will be negative. Yes or no? As x tends to 0 from the less than 0 side, y will tend to plus infinity. So we'll expect something like this. And this being the asymptote, we would, in order to produce monotonically increasing behavior, this is what would happen. And this would be the second root. These are the two roots, alpha and beta, of the numerator of this. This will be the graph of x squared plus 2x minus 1 by x, isn't it? Right? Make sense? Huh? Stand by.